In module 3.1, we defined expectation and variance, and we ended with an expression that we see here. Expected value of x is denoted by x bar, is integral of x multiplied by the probability density function f of x, integrated between the limits of minus infinity to plus infinity. X can take on any value between minus infinity and plus infinity. And similarly, the variance is expected value of x minus x bar squared. And the expected value by definition is the quantity times PDF integrated between the limits of minus infinity to plus infinity. And variance is standard deviation squared. S sub x was the sample standard deviation as we defined it. X bar is the mean value as we defined it. In this module, in module 3.2, what we will do is to derive some special relations, some important relations that gives us insight into what this expected value represents and what the variance represents. And it also gives us insight into some fundamental aspects of what we should expect when we have, in a design context, multiple random variables that together define a performance metric, and how the uncertainty in each individual variable will contribute to the uncertainty in our performance metric. So these are the relations that I'm going to go through and derive. C here is a constant. There are 4 important relations that I'm going to go through and derive. So C here is a constant. So expected value of a constant is a constant itself. Variance of a constant is 0. Remember, variance represents a spread. Expected value represents a central tendency. So if I have a single value, okay, this is not really a random quantity anymore, right? So if I have a single deterministic quantity, the expected value of that quantity, we intuitively expect to be equal to that quantity. Whether our formulae give us that quantity is something that we will verify in a minute. Similarly, we have an expression for expected value of a constant times a random variable x is constant times the mean value of x, and the variance of a constant times random variable x is c squared times variance of x. Expected value of a constant plus the random variable x is expected value of x plus the constant. Variance of constant plus the random variable x is nothing but the variance of x. And this last result is a very important result. Expected value of x squared is the standard deviation squared, or variance of x, plus the mean value squared. So I'm going to go through and derive these relationships. These are important. Okay, so let's start with the first relationship, which is expected value of a constant is equal to the constant. Variance of a constant is equal to 0. And in all of these derivations, we will use the fundamental property of the PDF, which is the integral going from minus infinity to plus infinity of PDF is equal to 1. One way to interpret it, as I said in the previous module, is what is the probability that x would lie between minus infinity and plus infinity? It's equal to 1. So that's one way to interpret the fundamental property of PDF. Expected value of any quantity, by definition, we said is integral going from minus infinity to plus infinity of that quantity times the PDF dx, and which is c times, owing to the property of the integration, this is c times f of x dx. And we know the integral of a PDF is equal to 1, because the probability of occurrence of x between minus infinity and plus infinity is 1. Therefore, expected value of a constant is equal to constant. Now, similarly, variance of the constant is, by definition, this is the definition, right? The variance of a constant integral going from minus infinity to plus infinity of the quantity minus its mean value, which is expected value of c squared. Okay, this is the definition of variance times f of x dx. And this, if we substitute, this is minus infinity to plus infinity, c minus c whole squared f of x dx, and that's equal to 0. Because the expected value of c, this quantity, is c. Let's move on to the second relationship. And the second relationship is that expected value of constant times a deterministic constant c times random variable x is equal to c times the expected value of x, and variance of c times x is c squared times variance of x. Expected value of c times x, by definition, is integral going from minus infinity to plus infinity quantity, which is c times x, times PDF f of x dx, which is c times integral going from minus infinity to plus infinity x times f of x dx, which we recognize, this quantity we recognize as expected value of x. Therefore, expected value of c times x is c times expected value of x. Variance of c times x, by definition, this is the definition, is integral going from minus infinity to plus infinity c times x minus the expected value of c times x whole squared quantity multiplied by PDF dx. Okay, so that is the definition of variance. Variance is expected value of the quantity minus its expected value whole squared. The expected value of that square is the variance. And this, again, I can write as integral going from minus infinity to plus infinity c times x and minus c times expected value of x whole squared f of x dx. And this is what expected value of x is what we denote as x bar. And therefore, I can substitute this as integral going from infinity, minus infinity to plus infinity, c squared. I can take out the c outside, make it c squared times x minus x bar whole squared f of x dx. And this is nothing but c squared times expected value of x minus x bar whole squared. Okay, this is what I recognize this quantity to be. Okay, and one intermediate step that might be helpful is I can write this as c squared times integral going from minus infinity to plus infinity of x minus x bar whole squared f of x dx, and I recognize this to be variance of x, or actually I recognize this to be expected value of x minus x bar whole squared. Remember, expected value of any quantity is quantity times PDF dx. And this, in turn, I recognize to be c squared times variance of x. Move on to the third example. So this is expected value of c plus x equals c plus expected value of x, and variance of c plus x is equal to variance of x. So let's do this. So by definition, expected value of c plus x is integral c plus x quantity times PDF dx, and that's by the summation property of the integral. So this is going to be c plus c times integral going from minus infinity to plus infinity of f of x dx plus integral going from minus infinity to plus infinity x times f of x dx. And this we recognize to be expected value of x, and this we know to be equal to 1. So this is going to be c plus expected value of x. And an important property of this is expected value of sum is always going to be equal to sum of expected value. Expected value of sum is going to be sum of expected value. So this in turn means expectation is a linear operator. You can think of expectation as a linear operator. So if I have expected value of, so in other words, expected value of x1 plus x2 and so on, xn, where there are n random variables, is going to be equal to summation over I of expected value of xi. Okay, so that is what I meant by expectation being a linear operator. So now let's go on to variance of c plus x, and that by definition is integral going from minus infinity to plus infinity of c plus x minus expected value of c plus x whole squared times pdf dx. And this is integral going from minus infinity to plus infinity c plus x minus expected value of c plus x we know to be c times c plus expected value of x, this whole thing squared f of x dx, and this is equal to integral going from minus infinity to plus infinity x minus expected value of x, which we can write as x bar whole squared f of x dx, and that is nothing but variance of x. So the linear operator property of expected value is something that we will use again and again. Maybe I should have written this as summation of expected value of summation of xi. Xi are random variables. Okay, they're also independent. The last derivation that we need to show is that expected value of x squared is nothing but variance plus x bar squared. Okay, or in other words, this is equal to variance of x plus expected value of x whole squared. That's the last derivation we need to do. Let's, in order to show this, let's start with variance of x. Variance of x is, this is by definition, expected value of x minus x bar squared. And so now I can write this as expected value of x squared minus 2 times x bar plus x bar squared. And this I can write at expected value. And I know that expected value of a sum is sum of expected values. Therefore, I can write this as expected value of x squared minus expected value of, and then expected value of 2 times x bar plus expected value of x bar squared. Now, once we have determined the mean x bar, the mean itself is deterministic. X bar itself is deterministic. We will say that x bar is deterministic. And therefore, the expected value we can write as expected value of x squared minus, now I can take the constant out because I know expected value of a constant times A quantity is constant times the expected value of a constant quantity. Now I can take x bar as a constant value because it's already been determined. There's no uncertainty to that. We'll assume there is no uncertainty to that. Plus x net plus we will have x, and then expected value of a constant is a constant, so I'm going to write it that way. Now this quantity is x bar, so this is expected value of x squared minus 2 x bar squared plus x bar squared, and therefore expected value of the variance of x is expected value of x squared minus x bar squared, and that in turn gives us the relationship that we seek, which is expected value of x squared is variance of x plus x bar squared. Now, in so far, I have not distinguished between population variance and sample variance, population mean and sample mean. And we will make that distinction as necessary, but for most of what we will do, we will not distinguish between them. We will not use mu and sigma as much as possible. We will instead use S sub x and x bar, simply because sigma is used for stress in mechanical systems, and so I'd like to retain that as much as possible, the notation sigma for stress. Okay, so this is the formula that we needed to prove. So we'll stop this particular module here.